Hi everyone, welcome to this video in which I'm going to go over proof. Now the first thing to note is that there's four types of proofs. There's firstly direct proof, which is also known as proof by deduction, and each step follows from the previous one using accepted fact and facts or results that are previously proved. And I'll show you a toolkit in a minute, and we can use that toolkit to help us with proof by deduction. Then there's proof by exhaustion, and this involves testing all the possible cases. Normally there's not more than 10 possible outcomes, so you can try all of them. Then finally to use a reasonable argument to justify your proof. Then there's proof by contradiction, and this involves firstly assuming the statement is not true, secondly prove that the assumption is false, and then hence the original statement therefore must also be true. And finally we get disproof by counterexample. That's quite straightforward. That's simply finding a case that doesn't fit the theorem, that doesn't fit the actual statement. So find one case in which the statement is not true and this is sufficient to disprove the actual statement. Right, so let's consider our toolbox, and these are various things we can keep in mind when we look at proof. Firstly, odd and even numbers. We know for any integer n, an even number is just simply going to be 2n for even, and 2n plus 1 for odd numbers. Multiples can simply be 3n, 4n, etc. Consecutive numbers can be written as n, n plus 1, n plus 2. Square numbers are naturally just simply n squared or n plus 1 squared, etc. Rational numbers can be written as a over b, where a and b have no common factors. Let's write that in, where a and b have no common factors. We will also have accepted facts, and these are things like the sum of angles in a triangle, perpendicular lines have a gradient of m, and minus 1 over m. So I'll just put things like sum of angles in a triangle, or our gradient, let's put that down as gradient of normal times gradient of tangent equals minus 1, something like that. Proven results and laws, well, that's things that we can take as standard are the indices, the index laws, we have the log laws, and also the discriminant. So things like d equals b squared minus 4ac determines the nature of the roots, and obviously trig identities as well. Okay, so these are things we don't need to prove, we can just take them as proven. And finally theorems, so things like Pythagoras' theorem, that's right, or the circle theorems. Okay, so these sorts of things are what we can use when we look at proof. Right, let's look at an example of a direct proof. So say we had to prove that every odd integer, so example 1, we had to prove every odd integer is a difference of two squares. So I'm going to write that down. Prove every odd integer is the difference of two squares. Okay, let's see how we can prove it. Firstly, an odd integer, so let's write an odd integer can be written as 2n plus 1. Okay, because 2n for any integer n. And so 2n plus 1, we want to think about the difference of two squares. And so with that end result in mind, we can write down, say, n squared. We can add an n squared to our 2n plus 1, and then subtract an n squared as well. And this, we can see that this part here will factorize into n plus 1 squared take away n squared. And so therefore, using some algebra, we've shown that every odd integer therefore is the difference of two squares. Okay, let's look at a disproof by counterexample. If we've got a case where it is suggested that for every prime number p, 2p plus 1 is also prime. We have to prove this is false. So by counterexample, we just need to find one case where it doesn't work. So let's try a couple. So if we put p equals 2, 2p plus 1 equals 5, which is prime. Okay, so therefore it works. And let's put p equals 3, 2p plus 1 gives us 7. This is also prime. This works as well. Put p equals 5, then 2p plus 1 equals 11. Turns out to be prime. Let's try p equals 7. 2p plus 1 equals 15, which is not prime. And therefore we can say the statement is false. So we found a case of a counterexample where that proof doesn't, that statement doesn't hold true. Right, let's look at a case where we have to prove by exhaustion. So say we've got a statement where we've got to prove that no square numbers, or rather no square number ends in an 8. Now obviously we can't go about and analyze every single square number, but we can think of the problem in another way. The final digit of any square number is really determined only by the final number of its square root. So therefore we can reduce the whole problem down to one-digit numbers. And if we start with, say, 0, so we've got 0 squared equals 0. So the square of any number ending in 0 it also ends in 0. 1 squared gives us 1. 2 squared gives us 4. 3 squared gives us 9. 4 squared gives us 16. 5 squared gives us 25. 6 squared gives us 36. 7 squared gives us 49. 8 squared gives us 64. And 9 squared gives us 81, and that covers all the particular cases. And we can see that there's no number here that ends in 8. Maybe I should just emphasize here that square numbers end in these particular digits: 0, 1, 4, 9, 16, 25, 36, 49, 64. So to give you an example, let's take this number 23 for example. 23 squared gives us 529. Now this 3 here, when we square it, gives us this 9 over here. And so therefore what we're trying to say is the last digits, these ones on the left, when we square these numbers, will give us these digits on the right as the final digits of the answer. And therefore we've proven by exhaustion that the final digits of an answer to a square number will never end in an 8. Right, let's now look at a case where we've got proof by contradiction, and in this method we assume the converse, i.e. the opposite of the conjecture is true, and then show that this leads to a contradiction. So say we had an example where we have to prove there are infinitely many prime numbers. So let's write that down. Prove there are infinitely many prime numbers. Okay. So the first step is to assume that this statement is not true. Okay, so let's assume therefore there are a finite number of prime numbers. Okay, and what we basically want to do is find a contradiction in this statement, and hence prove by contradiction that the original statement of infinitely many prime numbers is in fact wrong. So if we do have a finite number of prime numbers, then we can obviously list them. Let's say we can say so prime numbers, I'll say P1, P2, all the way to Pn. So I'll say there's a finite number of prime numbers. And right, so let's now create a number, and let's call this number Q, and say Q is made up of some numbers P1 times P2 times P3 all the way to Pn. Now naturally at this point, if I do Q divided by say P2, then that just gives me P1 times P2 P3 all the way to Pn. And so therefore there's nothing special about Q. Q is not a prime number. However, let's get rid of this. However, if we were to take this combination of numbers P1 times P2 all the way to Pn and add 1 to it, then by definition, if we then divide Q by any of these prime numbers, okay, then I will have a remainder of 1, and so therefore I don't have any other factors. So the only factors of Q are therefore Q and 1 itself. Okay, so here I've got a remainder of 1, and therefore Q is a new prime number, which is obviously not listed in my series of prime numbers that we had originally listed over at the beginning, and therefore I can say Q is a new prime number, and therefore there's obviously a contradiction in the fact that there's finite number of prime numbers. And we can therefore conclude that there are an infinitely many number of prime numbers.